All right, so now we've developed our approach for finding area in polar coordinates. Let's now take a look at some examples. We want to compute the area. So we're going to look at a simple example to start. R equals sine of theta. R equals sine of theta. So let's go ahead and graph this on Desmos. We're going to definitely use technology to help us with setting up and computing these areas. So we're just looking at the graph of r equals sine theta. So let me just get rid of some of these non-needed things here. For a moment, I'm going to take off the a and just leave that for its default. And its default is that this graph would be finished between 0 and pi. Now I'm going to go ahead and put my parameter a back on. So that tells me I need to go between 0 and pi, so I'm going to do that. 0 to pi, and again, I typically do an increment of pi over 12, which again works out to about 15 degrees. Okay, and I can zoom in here a little bit on my graph as we start graphing it. See at 0, the graph starts to swing out. Keep going. Here we are at pi over 4. You can see it's pi over 4 because it's a straight rectangle. All right, and we know sine's positive in the first quadrant, so these are all first quadrant things. Keep going. Now we're facing straight up at pi over 2. And we've constructed actually a half of this circle. And we keep going. And by the time we reach pi, we've actually completed the graph. We see that it's a circle. And we see that the area that was generated from 0 to pi over 2 is actually half of all the area because of symmetry. So what that means is we can actually cut down, if we want, on some of the stuff that we have to do. All right, so I could do the integral from 0 to pi. That is perfectly fine. Or I could take and cut it in half and say, hey, it's just going to be twice the area from 0 to pi over 2. And actually, either one works. Either one works. So that's up to you how you set that up. But we usually want to go with the graph and look at it first so we can see what limits we need to be dealing with angle-wise. So here, from that graph, which I'll just go ahead and paste it in there real quickly. Quick little picture of it. There it is. And we can see that we can actually get by starting here at an angle of 0, pi over 2, and then just double it. We could again go all the way around from 0 to pi. That would work as well. But I'm going to go from 0 to pi over 2 and double it. So 2 times the integral from 0 to pi over 2 of 1/2 f of theta squared. So sine squared theta d theta. So that puts me once again dealing with an integral of sine squared. So integral 0 to pi over 2 of sine squared theta d theta. Remember, we can't do that one directly. We have to use that. We either have to use a reduction formula if we have it at our disposal, or we have to use that sine squared identity. Right? Sine squared is 1 minus cosine theta over 2. Remember, the other one is cosine squared is 1 plus cosine. Oh, and that should be cosine 2 theta. Cosine 2 theta. Double the angle. Okay. So that's going to be 1/2 times the integral from 0 to pi over 2. So I factored the 1/2 out, and I'm just going to have a 1 minus cosine 2 theta d theta. And so integral of 1 is going to be pretty easy, but we're going to still deal with the integral of cosine 2 theta. So remember, we do a substitution. U equals 2 theta. du would call for a 2d theta. So this is going to look like this now. I'm going to drop my limits for a minute, just so I don't keep writing them all the time. So I'm going to drop that for a minute. So I'm going to have an integral of 1 d theta minus, and then here for this one, actually I should say 1/2. Don't forget the 1/2. Still there. And then cosine of 2 theta, I need a 2 to go with my d theta. So I would put that there and divide by it on the outside. So that would be 1/4 integral of cosine 2 theta times 2 d theta. And see how everything's set up. And we do our integral. Integral 1/2 1 d theta is just going to be 1/2 theta. Cosine is just sine. Integral cosine is just sine. So that's going to be minus 1/4 sine 2 theta. And then we want to evaluate this with our limits now, 0 to pi over 2. Okay, so sometimes I'll leave the limits off just to save a little bit of writing. Just remember that I'm going to come back to it later. Okay, and then we just need to evaluate this 1/2 theta minus 1/4 sine of 2 theta between 0 and pi over 2. So we would do that. We plug in pi over 2. That's going to be 1/2 times pi over 2. And then minus 1/4 of sine of twice that angle. Sine of twice that angle would be sine of pi, which is 0. So it's going to be minus 0. And then we plug 0 in. 1/2 of 0 is 0. Plug 0 in again. 1/4 sine of twice 0 is still just sine of 0. So in the end, we just get that the area of this circle is pi over 4. It's pi over 4. This original circle has an area of pi over 4. And if you look at it, it kind of makes sense, right? This is a circle, very clearly has a radius of 1/2. So pi r squared. Radius is 1/2, so pi times 1/2 squared would be pi times 1/4, which would be pi over 4. So that was a circle, so of course we could have computed that another way. And here we're just kind of confirming, yep, it works. It does actually work.